All right. We're going to very briefly, I hope, go through some other more elaborate algorithms that relate to Q-learning. So these are fancier than the basic algorithm. They're trying to do a little bit more, taking more into account. And in some cases, they're trying to take advantage of the nature of online learning and the abilities of other machine learning algorithms to incorporate them in here so that we can extend the kinds of problems we can work with. All right. So, I did want to just mention this. This is not a huge point, but um, when we evaluate reinforcement learning algorithms, we often are looking at um, the reward, the pattern of rewards that the agent gets. Because what we would like to see is that the cumulative reward grows. And you can also look at reward over time and hope that that is increasing as the agent goes along, that it actually is getting rewarded and not punished, and it's learning the correct results. If you know what the optimal result is, you can also compare the final outcome directly with that. Or you can do various kinds of analyses where you observe the agent and try to determine whether it's at what level it's performing. All right, what I really want to do is to look at these other algorithms. So there's an algorithm in your reading. It's called SARSA, and it's different from Q-learning in that it looks further ahead. So SARSA stands for State Action Reward State Action. Why? Because we update the table after we have all five of those. So we're not just looking at state action reward, update the table. We do state action reward. Now we're in a new state. Let's choose another action. And then we update the table based on longer context, basically. So it changes the discount term in the formula so that it looks at the next likely action rather than the maximum. So if you remember, I can scroll back up a ways. Here in the formula, we did look at the next state, and we just assumed that in that state, we would be choosing the thing that has the maximum action. What we do in SARSA is we look at the likely next action, however that's chosen, and we incorporate that into our update formula. So again, we're looking at more context than we had before. It's not that different than Q-learning. There are others. So there's this reinforcement learning model learning approach. Here, the observation is that online learning, oftentimes the learning agent is kind of stuck doing nothing while the environment does its work. So the agent says, I want to do action A, and then it has to wait for that action to take place and the result to come back. And that's a lot of time for a computer. So there's this lag time that, and the time that lag time, the time it takes for the environment to update, is fundamentally slowing down our algorithm. It can't learn anything while it's waiting for that to happen. So this model learning algorithm is trying to apply what we've learned already and fill the time while it waits for a result to come back. So this is a little bit of a funky approach, and I want to talk through it a little more detail than I maybe should. So what we're going to do is add a couple of extra tables. This is the Q table is the same as before. The C table here is basically what we were calling N before. It counts how many times we've been in state A and taken action in state S and taken action A. We're also going to set up another table that looks at in state S, take action A, get result S2. So we're going to count those separately. And then we're going to have another table, R of sub SA, which keeps track of the average reward we have seen so far being in state S and taking action A. All right, so one thing you might know is we're kind of unrolling the loop just a little bit here. So even before we start the rounds, we're going to observe the initial state S and choose action A, and then send that action to the environment. And that's mostly because we want the first step inside the loop to be what the agent does when it gets a response from the environment. because then the bottom of the loop is only happens when we get that response. So it's just kind of adjusting the loop to make that happen. It otherwise doesn't have a whole lot of importance to it. All right, so here we are. We get a reward and a new state from the environment. We're going to update our various tables. So we update T and C by adding 1 to the right place. We update R by incorporating the new reward into a scaled down version of the old reward. And then we're going to choose the next state. So we know now we're in state S2. We got that back from the environment. We're going to choose a new action for that state. And now this is the part where we're like, okay, I'm going to send the action to the environment, and then there's dead time. If this were our original Q-learning algorithm, it would just go around and then wait for the data to come back from the environment. Here, this little inner loop is adding in some learning while we wait for that to happen. If the environment responds quickly, it won't do much. If it takes a really long time, it'll do a whole lot. So what is it doing here? It's just randomly picking any state action pairs, and it's updating their Q values using a variation on the formula that we were looking at before. I'm not going to go into the details of this. You can go and look this up and look up the papers that talk about it if you really want to understand exactly why we update this way. But fundamentally, we're like, we already, we have updated information. Let's just spread it around to all of the other states and actions that might be impacted by it. So it's doing extra updates on just random other states and actions while it waits for a response from the environment. All right, so that's one thing. The next one is really like heading towards deep reinforcement learning, which is really big right now. And the idea is just, okay, the table gets unwieldy. If you have 5,000 states or 10 million states, 1,000 actions, this state table is just obnoxious. We just don't want to have to work with it. What if we had a machine learning algorithm manage that table for us? All we really need is something where we can give it a new example and it goes, okay, and adds that to its information. And we need it to be able to provide us with a prediction. So here we're in a state, tell me what action. Or here's a state in action, tell me what reward I'm going to get. That's actually how it works. So we could stick anything in there. Any kind of machine learning algorithm could act like that. You give it a new example and it learns from it. Or you ask it, here's a problem, give me a new prediction, and it can do it. So that was sort of an insight that led to reinforcement learning using neural networks in place of the table. So we have a learner who can either add a new example or predict. And here, the examples that we're talking about, the X, the input to the learner, is typically both S and A, the state and the action, and Y is the reward value. And then what we want is if we give it a state and action, it predicts the reward. It's fundamentally how we were using the Q table, but now it's an actual machine learning algorithm. All right, so this looks a lot shorter because more of the work is being done by our machine learning algorithm. We're going to figure out what state we are in initially. We're going to figure out an action. Notice that this is supposed to be learner. I think it just kept renaming it every time. Autocorrect is hurting me. So the learner is actually passed in, and we have the discount factor, which is the only piece we keep. So we select an action A, which could be by asking the learner about what we should be choosing. And then we repeat for some number of steps. We send A off to the environment, and we get back from the environment the reward and the new state. And then we say, okay, this is actually a SARSA algorithm, so it does this extra step of looking forward another step. It says select action A2 based on what the learner predicts. So we're in state S2. We want to think about A2. It's going to tell us a predicted value, and then we might ask it about a bunch of different actions and choose the one that's the best. And then we define a target. So we predict the reward we're going to get from choosing that action, scale it by our discount rate, add it to the reward R that we already got, and then that's what we actually tell the learner to learn. And then we loop. So this has this cyclical part. We've just really taken out the Q table calculations and let the machine learning algorithm do them instead. All right, I'm going to stop there. We're going to have one more short video.